Hi everybody, this little video is about charge basics. There's some definitions and concepts that I would think of as almost like background to understand the physics part of this. But you need to look through this and understand these words. We're going to use these words throughout this unit. And we'll learn lots of concepts and definitions in this video. So I hope that you will enjoy learning about these topics. Here's an objective describing what we're going to be doing here. What are some phenomena? What are some units that we use? And terms that we use to describe various electrical phenomena. So our basic topic is electricity, I suppose you could say. Here I have a fun photograph of what's called a Tesla coil generating an electrical spark. So I think we can all visualize an electric spark. But what is that spark? It may surprise you, but I'm not going to define the word electricity in this video. Usually when people say the word electricity, they mean electric current. In physics, we have a very specific definition for electric current, which we'll talk about later. But electricity is a little vague in physics terms. Anything that's electricity would have something to do with electric charge. So let's talk about what is charge. Charge is a little hard to pin down in words. It's some basic property of the universe that we can observe. Some things in the universe have this thing that we call charge, this aspect, a property, a characteristic that we call charge. There are two kinds of charge. You know this from chemistry. If you've had chemistry, you talk about negative charged electrons or positive charged protons or anions and cations as having positive or negative charge. And I'm sure you've heard of this before, that opposite charges attract. Opposites attract, very well-known thing that we learn about in science. Like charges repel one another, so two positives would repel one another, two negatives would repel one another, but a positive would attract a negative. How do we know that there are two kinds of charge? Here is a little hands-on experiment you can try. I hope that you'll actually do this. You can stop the video and try it yourself. All you need is some Scotch tape, the kind that comes in the little green package. Looks like this. And what you can do is charge the tape by taping it to something and then removing it. It helps if you kind of fold over one end so it's easier to get a hold of. And if you do a pair, watch this animation on the right, put a piece of tape on a table and then put another piece of tape right on top of it. And that's kind of like a tape sandwich. And then if you remove them and separate them, something interesting happens. You got to try it yourself. So I hope you try this experiment yourself. It's really easy to do. I wanted to show you what it looks like. Here's two pieces of tape on the table. I pull them off and then I separate them. And then over here I have a pencil. I'm just going to hang them on this pencil. And then here I have a single piece of tape. And hopefully you can see that some interesting things happen with these pieces of tape. Those are attracting, but these are repelling. Okay, so I hope you actually try this yourself. So get yourself some tape and try it. See if you can answer these questions. So charge the tape, make some comparisons. It helps if you label. On purpose, I did not label the pieces in my video because I want you to try this for yourself. But you can make an experiment, and what happens if I put a single next to a single, or a single next to a top, or a single next to a bottom, and so on. I can try all these various combinations, and do they attract or do they repel? What do you find? If you use like types, do they always repel? Can you figure out, is a single the same as a top or a bottom? It is one or the other. It's equivalent to one or the other. You should be able to convince yourself there are really only two kinds of charged tape, and they have this opposite behavior. Makes sense to say, oh, one is positive, one is negative. You might also try, I did not show this in the video, but you might try charging up some pieces of tape and then see if it attracts or repels a neutral object. A neutral object might be, say, your finger or a paper clip or another pencil or pen. So experiments like this were used to explore charge before we really knew what was going on. Here's a fun question. Can you tell which one is positive and which one is negative? I'm going to pause right here. You might want to pause the video, actually, and I'll give you some time to try this. But then I want to answer some questions, some of the questions that are shown here. All right, so what you should find is that the single is the same as the bottom. You should find that a single repels a bottom, a single attracts a top. Like charges always repel, opposite charges always attract. You should find that neutral objects are attracted to either one, or either one is attracted to a neutral object, and that might puzzle you a little bit. We're going to explain that. There's an explanation, but it's not super obvious why that happens. So once upon a time, this was all a little bit mysterious, but eventually, of course, we kind of figured out in science what's going on, and I'm sure you're familiar with some of these ideas. What is our modern explanation of charge? Well, the modern explanation is that, okay, all things in the universe that are made of matter have particles in them that are called protons and electrons. And typically, the number of protons equals the number of electrons. Not always, but usually. It is possible, however, for the number of protons and the number of electrons to be imbalanced. And then there is a net charge. And that is what we think is happening. So once upon a time, it was a little bit mysterious. Ben Franklin did experiments, and he's actually credited with giving the signs. Like, okay, I'm going to call this one positive, I'll call that one negative. But then eventually, people figured out the negative is this thing associated with particles we now call electrons. And positive is associated with these things we now call protons. When something becomes charged, like a piece of tape, what we think is happening is electrons are either going to the piece of tape or being removed from the piece of tape. So if we have a negatively charged piece of tape, it's because that piece of tape has more electrons than it does protons. If we have a piece of tape that is positively charged, then we think that somehow it has lost electrons. It is possible that you could add or lose protons, but if we're talking about atoms, that means you've changed the element. So that's not normally what's happening. Protons, of course, are locked away more or less in the nucleus of an atom, and electrons are free to come and go, but protons are not. So almost always, if we observe some sort of charge, it's because electrons have either been added to an object or taken away from an object. In chemistry, you talk about ions, and I don't know that it's fair to say that the tape was ionized, but it's a similar concept. We would say, okay, some of the atoms in the tape have either lost electrons or gained electrons, and that's causing my piece of tape to behave as a negative charge or a positive charge. One important property of charge is that it's conserved. Charge is a conserved quantity. So you've probably studied other things that are conserved in the universe, such as mass and matter. Energy is conserved, momentum is conserved, charge is conserved, and that basically means the total amount of charge remains constant, and here you see one way to say it, the net amount produced in a process is zero. So whatever you had to begin with, something might happen, but you're not going to create a new charge that didn't exist or some amount of charge that didn't exist previously. One thing that I might point out is that you might say to yourself, oh, well, okay, that makes sense. When there's a chemical reaction, I never change the number of protons and electrons. That protons can't be created or destroyed. Electrons can't be created or destroyed, but actually they can. Nonetheless, the charge is a conserved property. And the point I'm trying to make here is that charge is separate from particles. Charge is a property associated with certain particles, but charge, I want you to think of charge as a little bit mysterious. It's just a characteristic, and it is a separate entity, if you will, from the particle itself. I have some chemical or nuclear reactions actually here that I wanted to show you to illustrate this idea. So here's a reaction, decay of carbon-14. So you've probably heard of carbon-14. Carbon-14 is an unstable nucleus, and it can undergo a type of decay. That's illustrated by this reaction, and I've got it in picture form. So carbon-14 will kind of spontaneously emit an electron and a neutrino and become a different atom, nitrogen-14. So what does that mean? Well, before this decay, we have carbon-14, which consists of 6 protons and 8 neutrons. And then after the decay, we have these other things. So on the right side over here, nitrogen is element 7. It has 7 protons. And nitrogen-14 would have 7 neutrons. And then we also get this emission, electron and neutrino. So notice the protons, well, hey, I seem to create a proton. I have 7 now, and I had 6 before. I seem to create an electron. But if we look at the amount of charge, before we had 6 protons, and they each have a charge 1, positive 6, you might say, in chemistry terms. Afterwards, I've got these particles, these other particles. Before, by the way, my net charge would be 6. Neutrons don't add anything, they're neutral. But then after, I get these charges. So I have 7 protons and 1 negative electron. By the way, the neutrino is neutral. That's where the name comes from. 7 plus negative 1 is 6. So this is a reaction that illustrates the idea that charge is a conserved quantity. And it's conserved really anything that happens. This might seem like a kind of an obscure example, but I like that it shows that charge being the same before and after is separate from protons being the same before and after, or electrons being the same before and after. Here's another example. This is a different kind of decay, and I have sodium-22 becoming neon-22. And if we look at the breakdown, what happens this time is, hey, I'm missing a proton. Like I've got 1 less proton than I had before. And to counter that, we end up with this little particle that's very similar to an electron, except it's positively charged. It's called a positron. And if we check the charge amounts before and after, once again, we find, okay, yep, total amount of charge is the same. I get a different mixture of particles, but the charge was conserved. Okay, so moving on, we're going to talk about some types of materials that we need to understand whenever we're studying electrostatics. And those are insulators and conductors. Both of these things can be charged. They can become electrically charged. They could be positively or negatively charged, but there's a difference. And it's in the name. Conductor is called a conductor because it can conduct, i.e. allow charge to travel. Insulator does not allow charge to travel, or at least not freely. So we have the word freely in here. These are relative terms, but if you have a good conductor, then charge can easily flow through that. If you have a good insulator, then charge cannot easily flow through that. I bet you know something about this. I have two objects here. Which is the better conductor? Which is the better insulator? I bet you would correctly pick this answer. This is a metal bar. It's a better conductor. It's actually a really good conductor. It's an aluminum piece of aluminum, so that's a good conductor. Wooden block, pretty good insulator actually. So again, these are things you've probably heard of before. If we have a conductor, pretty much all metals are good conductors, but some other things are decent conductors too. We have a situation where the electrons can move. So from chemistry, you might recall this, that some electrons are tightly bound in an orbital, but others not so much. So in conductors, the metals, we have something sometimes called the sea of electrons, where electrons can move through the material. Those electrons in the outermost shells of that atom, or those atoms, are free to kind of come and go. In other situations, electrons are very tightly held into an orbit, and an atom would not give it up easily or take on extra electrons easily. If we look at the periodic table, 3 of the very best conductors, and I think this is illustrative of what's going on here, happen to share this same column right here. So I've highlighted copper, silver, and gold. Those materials are excellent conductors. Those are actually the most desirable conductors for electronics applications. Copper is in wiring all over the place. Pretty much all wires these days are made of copper. And then gold has applications in certain situations. It's an excellent conductor and also doesn't corrode, so it makes a good conductor in a switch. It's also used in electronics like cell phones. So these are excellent conductors, and notice they have the same column. So if they're in the same column, they have the same outer shell configuration. You might recall from chemistry, the outer electrons are not tightly bound to these nuclei. So that's essentially what makes them good conductors. Good insulators on the periodic table don't really show up on the periodic table per se, but your list of insulators would include things like rubber, plastic, wood, glass. Air is a pretty good insulator. Materials, and in these materials, these are typically compounds, and in the compounds, electrons are not easily transmitted. There's not this sea of free electrons like there is in metals. I have here kind of an illustration of insulator versus conductor. So you can charge up a piece of plastic pipe by rubbing it with a piece of wool. You'll see this demonstration. And that would be an insulator. So I've shown the pipe, and I'm imagining electrons just kind of sitting there. They can't move through the pipe, but they're stuck onto the pipe. And then I have this thing called an electroscope. And you might read or see electroscopes, read about or see them. An electroscope lets us do experiments to see relative amounts of charge on objects. And this has a section, all interconnected metallic pieces, and I'm going to highlight those in yellow here. So these parts are connected to one another. They're pieces of metal, and there's a piece in the center that's free to pivot. You might be able to tell there's a pivot point there, and that's a needle, and it's like an indicator. Okay, how much charge is there by this indicator? If we did an experiment with this setup, we could touch the top of the electroscope with the charge pipe. Let's do that and see what happens. So watch my animation. What we would see happen is the needle would deflect a certain amount after contact with the plastic pipe, and that would indicate a certain amount of charge had been present, and even if we couldn't see these charged particles on the pipe, we would know that charge was present by what happened with the electroscope. And what happens in the electroscope is based on the properties of a conductor. A conductor can be charged, the needle is charged, and it is charged due to conduction of electrons. So what happens is, watch this, here's another animation. When the pipe comes in and touches, electrons immediately spread out through this piece of metal. Wherever they can move to, they spread out. Why do they spread out? Well, like charges repel one another. And if you're an electron and you're bunched in with other electrons, you're going to push each other apart, and they're going to spread out. And then if you look at what's going on here, I now have this needle charged with electrons, and then the support stand is charged with electrons, and then that causes repulsion. And that's what's causing this deflection of the needle. So it's dependent on this being a conductor that this works. Here is something you can try yourself. You might want to pause the video, find these applications by searching on the internet, PHET, and then these titles, Johntra voltage, balloons, and static electricity. And they should be easy to find. These are very popular apps that can be run in a browser. All you need is any browser on any device, could be a phone or anything, and play with them. And then I have some questions. So look over these questions, open these apps, try it. I think you'll enjoy messing around with these. They're kind of fun to play with. But while you're doing that, you're hopefully showing some things that you need to be familiar with, including the difference between conductors and insulators. I have here a screen recording of the Johntra voltage app. And we're going to play this recording. Hopefully we can get this to work. And I have charged up my Johntra voltage, and then we're going to see the discharge. So something similar to this happen if you played with this application. And what's being illustrated here is the human body is somewhat of a conductor. Not the best conductor in the world, but charge can spread out. Did you get that much charge spread out on your Johntra voltage? You might try it, see if you can get that much charge to spread out. But then what we see happen is the spark, and the spark represents electrons jumping from the person to the doorknob. Why does that happen? Well, the electrons repel one another, and then there's a conductor nearby that they can travel through easily. So this is similar to what happened with the electroscope, but now we get a discharge to this doorknob. You've probably had something like this happen to you on a cold winter day especially. You notice static charge build up, and you might get a spark touching something metallic like a doorknob or a car door sometimes. So here we can run it one more time. Okay, so here is a screen recording I made of the other application, the balloons and the sweater. So let's watch this and talk about what's happening in this video. So we rub a sweater with a balloon, and we can see that's causing my balloon to gain electrons and my sweater to lose electrons. And then my balloons are acting in a way based on their charge status. So one thing that's interesting to note about this animation, I really like how this one is done. It clearly indicates properties of insulators. Notice the electrons do not spread out in the balloons. The electrons are stuck on one side. Also, the sweater. The electrons that haven't been transferred to the balloon are not moving through the sweater, which they would do if it were a conductor. So these are insulating materials. All of the materials shown here are illustrated as insulators. We also can see something interesting happening where the balloons repel one another. I'm going to play my screen recording one more time. but I got both objects charged, like charges, and you'll notice them repelling. Of course, the balloons are attracted to the sweater. So something else that's interesting that's shown here is conservation of charge. Whatever negative charge there is on the balloons, the sweater is positively charged an equal amount. The total charge is the same as when we started, a net charge of 0 if there were equal numbers of protons and electrons, still a net charge of 0. But the net charge of the sweater is positive, the net charge of the balloons is negative. Whatever amount the sweater is positive, the balloons together should be negative. One last thing to note here is the interesting behavior of the wall. The green balloon got stuck to the wall. And notice what's happening there. Within the wall, electrons are being pushed away from the negatively charged balloon, leaving a somewhat positive patch on the wall. And that is an interesting phenomenon we're getting ready to talk about. Without using the words, in the previous parts of this video, you have seen illustrated 2 ways that things can become charged. And this is some more vocabulary for you. You need to be comfortable with these words and using these words. One way that an object can become charged is simply by what we call conduction. And this is when charge is transferred from one object to another as a result of either being touched or, in some cases, maybe a spark occurs. For almost all situations, that's going to involve electrons. Electrons are carriers of charge, and electrons can definitely move from one object to another. If we see a spark, there are electrons causing the spark. Induction is more complicated to understand, but it helps us understand some interesting things that we observe. So induction means that there's been some sort of charge occurrence without a literal transfer. And typically what would happen is what's described here, that you would get a charge rearrangement of some sort because of the presence of a charged object nearby, or perhaps an external electric field. We'll talk more about electric fields later. I have these things illustrated, so let's look at some more animations to help you understand what's going on here. So we've already seen this. If I have this charged pipe and I allow it to touch something that's a conductor, then I can get electrons to come off of the charged pipe and, in this case, spread out in this conducting sphere. So suppose this is a metallic object. Electrons can spread out, and we saw electrons leave the pipe and go to the sphere. That would be conduction. Typically, if we have conduction, we would have a result that, okay, after the conduction occurs, these things are going to repel. My pipe has lost some charge, but not all of its charge. It's not a conductor, so parts of the pipe that were not touching the sphere could not lose electrons. It's still negatively charged, but now my sphere is negatively charged as well, a net charge of negative. So this would be charged by conduction. You've already seen it illustrated in some of the previous animations, the electroscope, the John Travoltage when his foot rubs the rug, or with the balloons, rub the sweater with a balloon, you get charged by conduction. Charge by induction looks like this. So I've got kind of the same setup, but suppose we do not actually touch the sphere, but instead we just bring the pipe close to the sphere. So what happens in that case is, because the sphere is a conductor, electrons would move away from the negatively charged pipe because those electrons are repelled by the negatively charged pipe. And what ends up happening is interesting. So like charges are repelling, but we have this positive section of the sphere which would be attracted to the negative pipe. Those positive section, that represents protons. Protons cannot move from the nucleus, so they're kind of stuck in place. So all of the protons are being attracted to the negative pipe. But if you think carefully about this, the protons are closer than the electrons after induction has occurred. And that's going to give us a net force, which is an attraction. And this explains why you can get neutral object like the sphere in this animation being attracted to a charged object. This happened in the previous animations, the balloon stuck to the wall. So whenever you see attraction occurring between two objects, it could be that one of them is actually not charged. It could just be a situation of induction. So induction can be kind of tricky, but induction is this situation where charge within moves, and that would, once again, typically be electrons that are doing the moving, and then I didn't actually have a transfer of electrons in this situation. On this page, we have some information about some details about charge. To quantify charge, we have a unit called the coulomb. Coulomb is named for a scientist who discovered something called Coulomb's law, and you'll learn more about that later. But for now, the unit that we use, this is like knowing that we can measure distance in units of meters or time in units of seconds. We can measure charge in units of coulombs. Some recent news with the coulomb: it was recently defined in a certain way. So a coulomb is basically a certain equivalent to a certain number of electrons, or alternatively, the amount of charge on one electron is a certain number of coulombs. And that's this quantity here, 1.602 10 to the negative 19th coulombs. That's a tiny amount of coulombs. There's a historical reason how it ended up like this. So that's an interesting story. You'll probably hear more about that later. But for now, you should be familiar with this, that, okay, charge can be quantified in coulombs, and it has this smallest possible value, this building block value, that found on either a proton or an electron. And here you can see at the bottom, an electron has negative that amount, and a proton has positive that amount. The symbol E is a symbol used in physics to represent this quantity, the charge on a single electron or proton. Q is our standard symbol for a variable amount of charge, just some random amount of charge that we might observe on something like a balloon or a charged rod. This concept that an electron has a particular amount of charge was investigated by a scientist named Millikan. You'll hear more about this experiment. He found something about charge, which is an important idea. He discovered that charge always occurs in these quantities, integer quantities of that value. At the time that he discovered it, that was not a known fact, but now we accept this as a fact of the universe, that charge always occurs in these amounts, some multiple of that smallest amount. That includes other things. It doesn't have to be protons and electrons. So we saw earlier a positron. There's something called a positron. It has plus that amount. There are other particles that occur, such as muons or pions or kaons, and these also have the same quantum value. So that's an important idea. And any amount of charge that's greater than that is a multiple of that. You can't have half that amount. You might have heard of quarks, but quarks cannot exist independently and remain. Quarks are thought to have 1/3 that amount, but if you can actually observe a charge, it's always going to be one of these multiples of this amount. Millikan's oil drop experiment went like this. A drop of oil might be observed, and then using some charged plates, Millikan was able to affect the motion of the drop of oil and then determine the charge on the oil drop. So in this situation, if a negative plate pushes up and a positive plate pulls up on the oil drop, then the oil drop must be negative a certain amount. The details of how that was determined we're not talking about right now. But Millikan was able to determine these amounts of charge, and then he made this discovery. Oh, look, that's a multiple of 1.6. So in this formula, Q equals N times E. N would be -5. And what that would mean is that this oil drop had a net charge of basically 5 electrons. Somehow it has 5 more electrons than it has protons. In other experiments with oil drops, he did this experiment over and over again. Sometimes he would discover an oil drop that you would need the plates to be the opposite polarity. Bottom plate positive, top plate negative, pushed up on the oil drop, indicating it has a positive charge. A positive charged electron would be an electron that has somehow lost, a positively charged oil drop would be an object that has somehow lost electrons. So if N equals 20, that would mean, okay, it's got 20 times the charge, the elementary charge, but that would mean that this oil drop had somehow lost 20 electrons and then had 20 more protons than electrons due to the loss of a certain number of electrons, that number being 20.